Welcome to Module 1 of Environmental Sampling, Control and Measurement. In this first part of the course, we will explore the reasons for monitoring exposures, how samples are collected and analyzed, the types of pollutants and classifications, and the principles that govern different sampling methods. We will also examine the fundamentals of air sampling, including particulates, gases, and vapors. By the end of this module, you should have a strong conceptual foundation in why and how environmental sampling is carried out. 1.1 Why monitor exposures? Exposure monitoring is essential because it allows us to evaluate risks to human health and the environment. By measuring pollutants, we can assess compliance with legal and regulatory limits, understand the scale and nature of environmental problems, protect workers in occupational environments, provide data for decision-making in environmental management and public health. Monitoring also gives us a baseline to evaluate control measures and identify trends over time. 1.2 What do we do with samples? Once samples are collected, they must be analyzed in the laboratory or sometimes directly in the field. Results are compared against standards, guidelines, or background levels. Data from samples are used for risk assessments, legal enforcement, epidemiological studies, development of pollution control strategies. 1.3 Classification of pollutants and sampling considerations. Pollutants are broadly classified into particulates such as dust, smoke, and aerosols, gases and vapors such as carbon monoxide, volatile organic compounds, and sulfur dioxide, biological contaminants such as fungi, bacteria, and pollen, chemical contaminants in soil, water, or food. For each pollutant class, the method of sampling must be carefully selected to suit the analysis method. For example, some pollutants require active collection using pumps, while others can be captured passively or with direct reading instruments. 1.4 Personal versus environmental samples. Personal sampling involves measuring exposures directly on the individual, such as through wearable devices or pumps. It provides an accurate picture of what the person actually inhales or comes into contact with. Environmental sampling measures pollutant levels in the general environment, such as air quality stations, soil monitoring, or water testing. This gives a broader context of contamination but does not account for individual variation in exposure. 1.5 Sampling systems and calibration. To ensure accuracy, sampling systems must be designed carefully. This includes choosing pumps, filters, sorbents, and collection media. Calibration is critical to ensure the flow rates and volumes are correct. Calibration is usually carried out against primary standards, ensuring that the readings are traceable and reliable. Decision matrices are often used in environmental monitoring to guide choices, such as when to use passive versus active sampling, or when to employ direct reading instruments versus laboratory analysis. 1.6 Air, particulate sampling. Particle transport basics explain how particulates move in air depending on size, shape, and density. Smaller particles remain airborne longer and penetrate deeper into the lungs, while larger particles settle quickly. Health effects of particulates are significant. Large dust particles may irritate the upper respiratory tract, while fine particles such as PM2.5 can reach the alveoli, causing cardiovascular and respiratory illnesses. Particle size selective sampling is therefore crucial. Instruments can separate inhalable, thoracic, and respirable fractions. Samplers include impactors, cyclones, and optical particle counters. Speciation of particles, such as identifying whether they contain heavy metals, organic compounds, or biological material, helps in understanding toxicity. 1.7 Air, gases and vapors. Monitoring gases and vapors requires specialized techniques. Active sampling involves drawing air through sorbent tubes or filters with pumps. The captured pollutants are later analyzed in the laboratory. Passive sampling relies on natural diffusion of pollutants onto a sorbent surface, useful for long-term monitoring. Direct reading instruments such as gas detectors provide real-time measurements of concentrations. Sorbent tube selection is vital because different sorbents capture different compounds. Activated charcoal, silica gel, and synthetic polymers may be used depending on the pollutant. Analytical equipment includes gas chromatography, mass spectrometry, and infrared analyzers. Applications include solvent monitoring in workplaces, auto exhaust testing, ambient air quality surveillance. 1.8 Other air sampling methods. Other methods complement traditional approaches. Emissions testing from smokestacks or industrial processes. Wipe sampling to assess surface contamination. Biomarker sampling that uses biological materials such as blood or urine to infer exposure. In this module, we established why exposures must be monitored, how pollutants are classified, and the distinction between personal and environmental sampling. We examined sampling systems, calibration, and decision-making in choosing methods. We also studied air sampling for particulates, gases, and vapors, along with their health impacts and measurement approaches.